So it is Tuesday, October 13th, 2020. Today we're going to be reviewing a little bit about displaying categorical and quantitative variables based on some of the work that I have graded, or the stuff that I graded last week. And then we're going to finish section 1.3 by discussing standard deviation and showing how to calculate that by hand with a small data set and kind of what it means in context. All right, so that's where we're going to start. Let's do that right here. All right, first, something I noticed while grading was that we need to kind of review bar graph versus histogram. Many of you totally get that a bar graph is for categorical variables and a histogram is for quantitative variables, right? That seems to be pretty clear. However, what starts breaking down is what they look like and what we can say about them. Right? So in general, they look pretty similar, right? They both have like an X and Y axis. In a bar graph, the horizontal axis shows our categories. Right? Like this example, we have field of study. So they like business, professional, other, arts, humanities, social sciences, education, and so on. On a histogram, the horizontal axis shows the range of possible values for the variable that we measured. Right? We have our frequency and relative frequency in the two graphs down here that we've seen previously. But on the horizontal axis, or the x-axis, we notice that we're going in order of the numbers. Right? And both of them, y-axis shows frequency. In a bar graph, the bars do not touch. They are separate things. Where one ends, the other one doesn't start. Right? That's because they represent separate things. In a histogram, the bars are touching because where the value of one bar ends, the value of the bar next to it begins. There's no space in between the numbers. Right? So that's why in a histogram, the bars should be touching. They shouldn't be separated by space. And that's to represent the fact that where one number stops, the next one begins right away. There's no gap. All right. The other thing, not just in like how to draw them, is that a bar graph cannot be described by a shape. I cannot say that a bar graph or a graph having to do with categorical variables has a skew to the left or skew to the right, or that it's approximately symmetric. It can't happen. And that's because I can put these bars in any order I want and create any shape I want. Right? I could arrange these categories, the fields of study, in alphabetical order, and the graph would look different. But I'm not misrepresenting the data, I'm just putting it in a different order. And I can, because there's no necessary order for those categories. It's not like numbers where I can't jumble the numbers. I have to go sequentially from 0 on up, right? So that's why in a histogram, I can talk about the shape, because the shape is unique to that distribution. Right? It has to be drawn in that order. I cannot put the bars in a different order without jumbling the numbers, which I'm not allowed to do. So with a bar graph, you cannot describe it with shape, center, spread, and those types of things that you can describe a quantitative variable with. Right? So you need to make that distinction. Though they look very similar, they cannot be described using the same vocabulary. And that was a very common mistake that I saw on one of the discussion boards, that the bar graph could be described as skewed to the right. It cannot be described as skewed or as any shape, because we could change the shape if we so choose to do that. All right? So I want to review that, make that clear. What questions do you guys have about the bar graphs and histograms? Does anyone need a minute to write anything down from this screen? All right, next screen. All right, another common error that I saw in the, I think it's the week 6 CYU is with the stem plots and skipping values in a stem plot. All right, so a quick review on stem plots. Stem plots are used to show the distribution of a quantitative variable. We have numbers. The stem can represent the number of tens, hundreds, thousands, etc. You just need to specify how to use the stem and the leaf in the key, and you can kind of play around with how they're arranged, right? The leaf represents the second digit or another digit of the number. Right? A key is needed to read the stem plot and interpret the values. You can't just build a stem plot and assume that the reader will know how to read it without providing a key. Right? Numbers cannot be skipped in the stem. Right? You have to treat the stem, right, this middle lane here, like a number line. You can't skip numbers in a number line. It wouldn't make sense to draw a number line, like for a dot plot, and go 0, 1, 2, 5, 6, 8, 9. Right? Just because I don't have a dot to go with a number doesn't mean that I get to leave it off the number line. If I only included the numbers I needed, my graph would not be an accurate representation of the data and the shape would be off. Same thing happens with the stem plots. Right? We have a regular stem plot over here for graph A, where it's just the stem 0, 1, 2, 3, and the numbers that finish that stem. Right? So in this data set, we have 4, 5, 5, 5, 6, 7, 7, 7, 7, 8, 10, 10, 10, 10, 11, 12, 14, 22, 35, and 38. Okay. The next one is a split stem, where now we split each stem into 2 rows. So we get 2 spots for 0, 2 spots for 1, 2 spots for 2, 2 spots for 3. It's representing the same data as in graph A. But the first row only gets leaves from 0 to 4. The second row gets the leaves from 5 to 9. And then 0 to 4, 5 to 9, 0 to 4, 5 to 9, 0 to 4, 5 to 9. Even though this row has no values, I have to write the 1. I can't skip it. If I skip it, then I'm not using the same scale along the graph, along this representation, and my representation will be off. It will not be accurate. Right? So that's why many of you maybe got that question wrong on the week 6 CYU. It's because you decided that you could omit numbers that weren't being used. Just because they're not being used doesn't mean you don't have them. They must be included in the stem. All right. And then over here we have a back-to-back stem plot with a split stem. Okay. Are there any questions about the stem plots?
No.
No? Okay. All right. Does anyone need a moment to write anything down from this slide? Please raise your hand. Okie dokie. Another thing that I want to stress again is what you write and how you write it matters. Right? The graders of the AP exam or the AP Stats exam will care about how you write your answers. Be specific and write with good grammar and overall structure. You need to write complete sentences, right? They need to have a beginning, middle, and end, complete thoughts, right? And use good grammar. The graders assume that you are writing at a college level because you're trying to get college credit. Okay? So you have to write professionally, so to say. You need to say what you mean. Don't leave things up to interpretation. Right? This goes back to being specific. Right? Consider the 2 sentences here. First one, we have the range of the numbers is 8. Well, that might be accurate. That might be the range. Cool. We have the second sentence here. The range for the height of the players is 8 inches, and all the players' heights are between 68 and 76 inches. I've described now the spread with more detail, right? And I know that I'm talking about height of players. I'm talking about inches as far as the units. Right? I know what the spread, the overall spread is, like the range from 68 to 76, and right, the range of 8 inches is represented. I've given lots of detail and specifics. All right. One is, they're both correct. They have the range, but one would receive a much better score than the other. Right? You have to be specific and you have to provide the details. All right. Now, this is something I'm going to continue to stress. I'm going to continue to give you feedback like, hey, please write complete sentences. All right. Write properly. Don't, if I can't make it through your sentence, like it doesn't make sense, you need to rewrite it. All right. I say this out of personal experience where I took what you would consider a high stakes exam that had a large writing component, and I did not pass that exam the first time I did it, not because I didn't have the right answers, or not because I didn't have good content, but because I didn't write it well enough. That was the only issue. And so I had to pay to submit that test again with a rewrite where all I did was add extra flowery details and little specifics here and there, but I didn't actually do any new work. All right. But the second time, with the more flowery writing and more specific writing, I got a better grade and I passed. Okay. Just an example. This matters. Okay. I'm not just making stuff up. All right. So even though it's a math class, you have to write at a college level. That will be the expectation when you're in college. Right? The professors assume that you can write at a college level, and if you're not, it's going to hurt. You're not going to get the grades you feel you deserve. It's not because you don't know the content, but it's because you cannot say what you understand in a professional way. So that's what we're going to be continuing to practice in this class. The way that you write your answers is important. The last thing on the slide, normal versus symmetric. For now, distributions that look symmetric will be called roughly symmetric or approximately symmetric. Being normal or approximately normal only applies to special distributions, which we will learn about in chapter 2. Okay? To be a normal or approximately normal distribution, you have to fulfill certain criteria. Right? We haven't seen what that is yet, so we cannot use that term. We can say something looks symmetric, or is roughly symmetric, approximately symmetric. Even if it looks normal, like a normal curve, we cannot call it normal yet because we do not know what the characteristics of a normal distribution are. That's an error in how the previous classes, as far as like Math 1 and Math 3 were taught, where the textbook said things were approximately normal when they had that bell shape or they had a symmetric curve. That's an issue with those textbooks, so I do apologize. But for now, we cannot use that term. Okay? Is there anything I can clarify on this screen? All right. So then, we can switch gears. All right, now into the lesson for today. As far as standard deviation goes, if you're taking notes, now's the time. So again, this is the same definition that you were given at the end of class last Tuesday that I just went to very briefly, and I showed you on the calculator how to find standard deviation once you've input. There we go. Once you've input your data into a list, right? We're going to show how to calculate standard deviation by hand. It really only makes sense for a small data set. The data set we're going to do the example with has 9 data points or 9 observations, and that is manageable. We can do that. And again, measuring spread, the standard deviation. A standard deviation is another way to measure how spread out my data is. That's the whole point. How varied is it? Right? The standard deviation and the variance measure spread by looking at how far the observations are from their mean. Right? Our previous way of measuring spread is with the range, which is the entire range of all of our numbers. It doesn't have to consider a mean or median. Then we have the IQR, or the quartiles, interquartile range, and that depends on the median to find that number. Okay. This next one is the standard deviation and variance depend on the mean. So depending on the measure of sensor you're using could change how you're measuring spread. Right? So this one has to do with the mean. We're getting into a lot of notation here. Don't get stressed on the notation. It will make much more sense once we do the example. Right? Standard deviation, S sub x, and variance, S sub x squared. The standard deviation, S sub x, measures the typical distance of the values in a distribution from the mean. Whenever you see this word typical, it's essentially saying the average distance. It is calculated by finding an average of the squared deviations and then taking the square root. This average squared deviation is called the variance. In symbols, the variance, S sub x squared, is given by this crazy set of letters. Right? But essentially, all the variance is saying is take my first observation, subtract the mean, and square it. Then add the second observation minus the mean squared, then add the third observation minus the mean squared, so on until you've done all of your observations minus the mean squared. Add those numbers up, divide by n minus 1. We don't divide by n because we need to have that minus 1 to account for the fact that we're dealing with a sample set and not the actual population. Right? If we divided by n, it would make our deviation it would be inaccurate, so to say, and would not be close enough to where we need it, as if we were to have the entire population. So we have to do this minus 1 to account for that error, so to say. And once we have this variance number, we simply take the square root of it to find the standard deviation. That's this last formula at the bottom. S sub x equals the square root of the variance. It's a lot of symbols. We're going to do this example, and it hopefully will help this make a little bit more sense. Right. So the first step is we need the mean. If we don't have the mean, we can't find the standard deviation. So I'm going to do a couple of things first here. So we have our data set. Right. Below is the number of pets owned by 9 children. They have already been arranged from lowest to highest. Excellent. So we got 1, 3, 4, 4, 4, 5, 7, 8, 9. We're going to use this data to practice finding our standard deviation. First, I'm just going to make a basic dot plot so that we can see what it looks like visually. So we have our number line here. It's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Just too bad. We have a data point at 1, 1 at 3, 3 at 4, 1 at 5, and then we have 7, 8, and 9. All right, cool. That's what our data set looks like. Now we're going to find the mean. We'll use the kind of the notation here. We're going to call the mean x bar. We'll add up all of our numbers and divide by the amount of numbers we have. So we have 1 plus 3 plus 4 plus 4 plus 4, 5, 7, 8, 9, all divided by 9. equals 45 divided by 9, which leaves us with a mean of 5. Which also tells us that on this distribution, on the graph, we can consider 5 kind of the balance point. Right? So now we're starting to build all the data that we're going to need. Right? We've got our mean. We can see where it is visually. We've got our balance point. Now that we have the mean, we start the steps here in how to find the standard deviation. We're on step 1. Find the distance of each observation from the mean and square each of these distances. Right? The best thing we can do is keep this organized. So we'll do like a little table. And the first thing will be observations. Then the difference, or not difference, distance. Distance from the mean will be our second number. And last, we will have the distance from the mean squared. Next, so we'll list our observations. We have 1, 3, 4, 4, 4, 5, 7, 8, and lastly 9. And to find our distance from the mean, we'll just subtract the mean from the observation. So we have 1 minus 5, that equals -4. 3 minus 5, -2. 4 minus 5, -1, -1, -1. 5 minus 5 will give us a 0. 7 minus 5, 2. 8 minus 5, we get 3. And 9 minus 5, 4. And now we take the numbers from the distance from the mean and square them. Right? -4 squared, we get 16. -2 squared, 4. -1 squared, we get 1. 1 and 1. 0 squared is 0. 2 squared, we get 4 again. 3 squared, 9. And 4 squared, we get 16. So what we've just done in this table is we found the numbers that go in the top of this equation. Right, we're going to add these numbers, the distance from the mean squared, and then divide that by n minus 1 or 9 minus 1 to find our variance. Right, so that's our next step. And we use the notation here. We will find the variance, right, s sub x squared. And we'll do that by adding up our numbers. We have 16 plus 4 plus 1 plus 1 plus 1 plus 0. 4, 9, and 16 divided by 9 minus 1. And that lands us at 20, 30, 49, 52. Divided by 8, which is 6.5. That number is the variance. All right? Now we have our variance. We have this number, right? So that was step 2, average the distances by dividing their sum by n-1. Boom, done with that. Step 3, standard deviation f sub x is the square root of the average squared distance, which is the square root of the variance. Let's pick another color. We have s sub x equals square root of 6.5. which is approximately 2.55. And this is our standard deviation. Okay, so we have now calculated our standard deviation. We've got our variance. We've got all these numbers now. What does this tell us about the context? So ultimately, we have to relate this number back to our context. Standard deviation and variance both tell us something about how spread out the numbers are. The smaller the standard deviation, the closer our numbers are together. The farther away, the bigger the standard deviation, the more spread out everything becomes, right? So when the standard deviation is small, there's less variability in our numbers. Within this context, this essentially says, right, the number of pets, because we're talking about the number of pets, these kids have typically varies from the mean approximately 2.55 pets. Now, obviously, that's kind of an odd number to assign to pets, but it essentially means that, like, our average number of pets owned is 5. Typically, the students will have somewhere between, let's see, 5 minus 2.5, 2.5 to 7.5 pets, right? Which doesn't really make sense, so like 2 to 7 maybe. But it gives us an idea of the spread, the variability of the answers. Okay. So, what questions do you have?
So you only use this when you have like a small set amount of data?
You would only most likely be asked to do this by hand with a small set of data, right? Because our calculator will find the standard deviation for us when we put all the numbers in a list. With larger data sets, we're not going to do this, right? If I had 50 data points, this would take forever to do by hand, right? And it's not worth it when our calculator does it. We need to know where it comes from, because it's entirely possible you might be asked to take a small, like 10 number, 15 number, even data set, right? And find the standard deviation. And you may need to show how you did that by hand and not just be able to do it on the calculator. So we have to review it. I have to show you. And it also gives us an insight as to what it means, right? We're finding where all of our calculations have to do with the distance from the average or the distance from the mean. Right? So we're using that mean as kind of our guidepost for how spread out everything is. Whereas the other method we have is using the median and the IQR to find how spread out things are, or quartiles, so to say. Which leads me to my next point. We can also use the standard deviation, similar to how we use the IQR, to identify outliers or possible outliers. Right? So we can say, this is a general statement, we're not going to use this really right now, but it's something that will come up later in identifying outliers. So we can say possible outliers are greater than 2 standard deviations, and I'm just going to write SD for standard deviations, from the mean, or less than 2 standard deviations below the mean. Yeah, I need to change that word. Right. Possible outliers are greater than 2 standard deviations above the mean, right, to the right of the mean, or less than 2 standard deviations below the mean. This is, again, kind of like just a general rule similar to the IQR times 1.5 to give us boundaries on the high end and the low end of a distribution to where, okay, when things are outside these boundaries, they could be considered outliers. And so this is a general rule using standard deviation. In our example problem here, we don't have any possible outliers because 2 standard deviations is going to be just a little more than 5. When we add 5 to the mean, we get 10. We don't have any values greater than 10. And subtract 5 from our mean, we get 0, and there's no values less than 0. So in our given example here, there's no possible outliers. Okay. What else can I clarify? Does anyone need another moment to write stuff down? Please raise your hand. All right. Okay, so then, real quick, let's take a look at what our week looks like. All right, here we go. We're on week 8. All right, we made it through Monday. It's now Tuesday. We're on our live class meeting day. We are finishing section 1.3, which is the end of chapter 1. All right, we are officially done with chapter 1. I'll be updating our live class resources with the notes from today and the recording of our live session later today. We have a discussion board for today that will have you basically do the same thing that we just did in this example with another set of numbers, except this only has 5 numbers in the data set, so it shouldn't be that terrible. All right. Thursday, we're going to start chapter 2. Which means I'm going to make the chapter 1 self-assessment available later, hopefully later today, but if not, tomorrow morning. So you guys can start working on that. And keep in mind, self-assessments are weighted higher, right? They carry more weight than the other assignments that we have. So if you have to pick and choose, do the self-assessment. All right. This will have the same overall format as Chapter 4 self-assessment did. There will be a demonstration of understanding, a reflection, and a self-assessed grade portion. Okay, and then we'll start Chapter 2 on Thursday. We will be kicking that off, kind of talking about percentiles and identifying the location of data within distributions. And so that's essentially what the week looks like. Yeah. Anyone have any questions, or can I give any clarification on this week? All right. Nah, okay. Thanks, Valentine. All right, so then that is the lesson. All right, that's it. I think I made it at like 40 minutes, almost like right on time. So if you have any questions, please feel free to stick around and ask them. But if you are happy with where you're at right now, and you have no questions, you're ready to rock and roll and get on with your day, you are free to go. I hope you'll have a great rest of your day, and I'll see you on Thursday.